robotic exploration of the moon. The moon has held our imaginations for millennia, yet it is only in modern times that we have visited this body, first with robotic machines and then with astronauts. Exploration of the moon has taught us much about the evolution of the solar system and ourselves. We've known for centuries about the effects on tides and biological cycles from a waxing and waning moon. But it took space-age exploration to show us how the moon is connected to human existence on a very fundamental level. The space age arrives, robots, to the moon. With the shocking launch of Sputnik 1 in October 1957, the moon changed from a distant silver disk in the sky to a real place, a probable destination for probes and people. The Soviets struck first, flying Luna 1 by the moon in January 1959. They followed this success with a number of other robotic probes, culminating later the same year with Luna 3, which photographed the far side of the moon, never visible from Earth. From these early, poor-quality images, we discovered that the far side has surprisingly little of the dark, smooth mare plains that cover about a third of the near side. In response to the 1961 flight of Soviet cosmonaut Yuri Gagarin, President John F. Kennedy committed the United States to landing a man on the moon by the end of the decade. The Apollo program greatly accelerated interest in exploring the moon. To ensure that human crews could safely land and depart from the lunar surface, it was important to understand its environment, surface, and processes. At the same time, the robotic precursors would collect valuable information, constituting the first scientific exploration of another planetary body. We got a much closer look at the moon's surface in early 1966. Again, the USSR led the way by safely soft landing the robotic Luna 9 spacecraft on the Mare Plain, Oceanus Procellarum. It found the surface to be powdery dirt strewn with a few rocks, but strong enough to support the weight of a landed spacecraft. In May 1966, the United States followed with the landing of the complex robotic spacecraft, Surveyor 1. It sent television pictures back to Earth, showing the surface and its physical properties in detail. Later Surveyor missions, 5 in all, collected physical data on soil properties, including its chemical composition. Analysis of the lunar surface showed that the dark Maria had a composition similar to terrestrial basalt, a dark iron-rich lava, while the highlands near the very fresh-rayed crater Tycho were lighter in color and strangely enriched in aluminum. This led to an astonishing revelation about the moon's early history after the first physical samples were later returned to Earth by the Apollo 11 crew. In November 1969, Apollo 12 touched down in Oceanus Procellarum, Ocean of Storms, near the previously landed Surveyor 3 spacecraft. This mission demonstrated our ability to precisely land on the moon, a skill critical for navigating to future sites in the highlands and rugged areas. Astronauts Pete Conrad and Alan Bean explored the site in 2 moonwalks. They collected over 75 pounds of samples and deployed a nuclear-powered experiment package. Lavas from this landing site are slightly younger than those of Apollo 11, but still over 3.1 billion years old. The highland component here is different from that of the first landing. It has an unusual enrichment in radioactive and rare earth elements, suggesting that the moon's crust is laterally variable and complex. As a bonus, the crew also returned a light-colored soil, possibly part of a ray cast off and flung outward during the formation of the distant crater Copernicus, 186 miles north of the landing site. Dating of glass from this soil suggests that Copernicus is only 900 million years old. The explosion of an oxygen tank on Apollo 13 prevented it from landing on the moon. The 3-man crew returned safely to Earth, a memorable saga closely followed around the world. Apollo 14 was sent to a highland site east of Apollo 12 near the ancient crater Fra Mauro. This site was chosen to collect rocks blasted out from deep within the moon by the formation of the giant Imbrium impact basin. a crater over 620 miles in diameter and situated 3,123 miles north of the landing site. Astronauts Alan Shepard and Edgar Mitchell conducted 2 moonwalks on the lunar surface. Towing a pull cart filled with tools, they returned over 95 pounds of rock and soil. Samples from the Fra Mauro highlands are breccias, complex mixtures of ancient rocks, broken and crushed by the giant impact that created the Imbrium Basin. From these samples, scientists learned the Imbrium impact occurred more than 3.8 billion years ago, before the dark mare lavas flooded the moon's surface, but well after the formation of the moon's crust over 4.4 billion years ago. After this third landing, a new picture of lunar evolution was emerging. The moon was not a simple lump of cold meteorite, nor was it an active volcanic inferno, but a planetary body with its own complex, subtle history. The future and significance of lunar exploration. Now we are preparing for humanity's return to the moon. Over the next couple of years, at least 4 international robotic missions will orbit the moon, making global maps of unsurpassed quality. We will soft land on the moon, particularly the mysterious polar regions, to map the surface, examine the volatile deposits, and characterize the unusual environment there. Ultimately, people will return to the moon. The goals of lunar return this time are not to prove that we can do it, as Apollo did, but to learn how to use the moon to support a new and growing spacefaring capability. On the moon, we will learn the skills and develop the technologies needed to live and work on another world. We will use this knowledge and technology to open the solar system for human exploration. The story of the moon's history and processes is interesting in its own right, but it has also subtly shifted perspectives on our own origins. One of the most significant discoveries of the 1980s was the giant impact 65 million years ago in Mexico that led to the extinction of the dinosaurs, allowing the subsequent rise of mammals. This discovery, made possible by recognizing and interpreting the telltale chemical and physical signs of hypervelocity impact, came directly from the study of impact rocks and landforms stimulated by Apollo. Scientists now think that impacts are responsible for many, if not most, extinction events in the history of life on Earth. The moon retains this record, and we will read it in detail upon our return. By going to the moon, we continue to obtain new insights into how the universe works and our own origins. Lunar exploration revolutionized understanding of the collision of solid bodies. This process, previously thought to be bizarre and unusual, is now viewed as fundamental to planetary origin and evolution, an unexpected connection. The final robotic missions mapped the entire moon from orbit for the first time and obtained extremely high-resolution pictures of potential landing sites, certifying their safety for the Apollo missions to follow. This U.S. Lunar Orbiter series conducted 5 mapping missions, whereby boulders as small as a couple of meters could be seen. They also obtained amazing views of scientifically interesting targets, such as the first pilot's eye view of the large, brightly rayed crater Copernicus, dubbed the Picture of the Century by news reporters. More pictures of the century were soon to be obtained by people walking on the moon. From these robotic missions, we learned that the moon was cratered and pitted at all scales. The surface was powdery dust, but strong enough to support the weight of people and machines. The moon had no global magnetic field or atmosphere and was made up of common rock types, similar to those found on Earth. Now the stage was set for the next giant leap in understanding lunar and planetary history.